Hi everyone, my name is Phil Lambert from Fortify, located in Boston, Massachusetts. We're here again at IMS in 2024. We've got a great booth on display this year, a bunch of cool new parts that I'd like to show off, and I'm going to get started here with this horn lens here from, we co-designed this with Teltrium, one of our partners. This is a horn lens that sits in front of a horn antenna, and it helps to do phase correction to the radiation coming out of the horn, giving this horn antenna about 2 to 3 dB improvement over the frequency range of that antenna. So now I'm going to move on to another lens, another antenna just over here across the booth. Now I've got our second device I'd like to show off. This is a field of view enhancing lens. This lens is sitting on top of an Anoki-Wave, now Qorvo, phased array antenna. What this lens is designed to do is take the field of view of your phased array that in this situation is plus or minus 60 degrees from boresight, and it takes that 60-degree beam and turns it out to 90 degrees. So what you're doing here is essentially taking an antenna that has a field of view, a field of regard of 120 degrees, and turning it to 180 degrees, significantly improving the field of view for this specific antenna. So the value proposition for this lens is it significantly improves the field of view, which when you're going into your mission, reduces the number of antennas you need to deploy to cover the same amount of sector or the same amount of the region you're trying to cover. Not everything we do is antenna-based. Some of our customers are taking advantage of our very low-loss materials that we can 3D print to create chip fixtures. So these are fixtures that are holding microchips in place during inspection and diagnostics. We designed this chip carrier with our partner at Menlo Micro. We have a really great case study that just came out, so you can read all about the value proposition for these chip carriers in your testing and diagnostic and manufacturing applications. We're really excited to show off this antenna too. This is an end-fire antenna. It is a dielectric polyrod antenna that we designed with Iris, which is one of our design partners in the defense and aerospace sector. What's really unique and really interesting about this antenna is that it has this integrated radome on top of the polyrod. So there's a dielectric polyrod on the inside here, and it's 3D printed with an integrated radome that we then coated and matched with this waveguide feed. So we're really excited about this really cool end-fire antenna that can be used for for material testing, point-to-point communications. It's really high gain and an excellent antenna for all types of applications. This is a really cool one, brand new this year. This is a lens that we designed as part of the Navy program where we are combining our high dielectric sintered alumina material with our low loss polymer dielectric material to create a single assembled hybrid lens that allows you to go from a very low dielectric at the surface near 1 to a very high dielectric in the middle near 5.6. And that allows you to compress the size of this lens all the way down to just 1.5 inches in height to do all the same phase shifting that you might need to do with a lens of similar size over here. And so the benefit of this is that we're able to leverage those high dielectrics and really shrink the profile of this lens for applications in UAVs, anywhere where you need to reduce the profile of your lens for a high gain switched beam antenna type architecture. All right, that's it from me. Now I'm going to hand it off to my colleagues Henrik and Jeff, who are going to walk you through the first live demo Fortify's ever had at IMS this year, and I can't wait for them to walk you through it.
Hi everybody, my name is Jeff von Leska. I'm an applications engineer at Fortify, and I'm really excited to be able to show off this point-to-point demo that we have set up here. So what you see here is a Lüneburg lens placed in front of a waveguide. We have it scanning from 20 to 24 gigahertz, and as you can see, without any extra power added to the system, we get about 18 dBi of gain enhancement just from the lens. This could be really beneficial in point-to-point systems, high-power lensing systems such as 5G wireless backhaul and ground-to-satellite communication systems. So here we have a cross-section of the lens that's on the demo, and as you can see, the taper from the core to the edge of the lens produces dielectric ranging from 2 to 1.2 on the edge, and this is what creates that Lüneburg distribution and provides the gain enhancing properties of these types of lenses. So we also have this ceramic lens. This is again a Lüneburg distribution within the lens and produces a similar gain enhancement to the radix lens, but it's really valuable in high temperature applications where the radix might not survive. And so as you can see, we put that in the system, and again we have a similar 18 dBi of gain enhancement. So with a bulk dielectric constant of 8, developing the lens with the ceramic material really opens up a wider envelope of design freedom to fine-tune and control the antenna systems that you're designing the lens for. Again, my name is Jeff Von Leska, Applications Engineer with 3D Fortify. If you have any questions or would like to learn more, please reach out to us at 3dfortify.com. Thanks.